dispersion.
So good afternoon. I would like to present on behalf of Prof. Chao on this climate modeling and analytics for urban heat risks, mitigation, and adaptation. And we are from the Urban Climate Design Lab from the Department of Architecture in National University of Singapore. And I would briefly show some works in our lab, and all the vision of our works is to build climate resilience for people who live in cities and people who live in areas with heat risks from climate change and urbanization. So the mitigation strategies of our works work in three different skills and with different tools, but they are consistent and systematic with each other. So there are three scales. First is the urban scale, then neighborhood scale, and building scale. And at the neighborhood scale, the attention is to delineate the air paths and basically using a GIS-based tool. While at the neighborhood scale, we focus more on the microclimate, more localized microclimate using the high fidelity CFD simulation. And while at the building scale, we focus more on how building design will impact the microclimate. So at the building scale, there are mainly two heat risk factors. They are climate change and urbanization. And we look at the climate change first. The station, which located at the rural area of Singapore, which is Palawubing area, was chosen as the target station to exclude the impact of urbanization. And we combined the field measurement and the regional scale model to investigate the city scale impact of climate change. And the results show that, and we make projection for 2020 to 2099, and the projection shows that there will be up to 0.6 Celsius degree in air temperature increment by 2030s. And the second factor is the urbanization. According to the National Environment Agency in Singapore, that the mean temperature difference between two stations, let's say the most urbanized station, the Newton station, and the other one is the least urbanized area station, which is the Palawubing station, the difference are becoming larger year by year. And this map shows the distribution of air temperature increment due to the pure urbanization from now to 2030s. And we estimated through a linear regression between air temperature increment and the elevation activation of the station and the gross plot ratio around the station. And we can see that the areas with substantial increase in plot ratio shows more pronounced air temperature increment. So that is to say by 2030s, Singapore will experience about 0.6 Celsius degree increase in the air temperature due to global warming, and additionally another 0.8 Celsius degree by pure urbanization. And zooming in further, we also look at the effect of urban heat island brought about by the urbanization. So based on the field measurement data and the sky view factor data of the stations, we develop a linear regression between air temperature increment and sky view factor and use it to map the whole Singapore as shown on the left map. And this urban scale map indicates the main urban belt with high UHI intensity lies in the east-west belt. And in this way, we can see that the open spaces like the reservoir and air base play an important role in separating the UHI cluster as well as to introduce the monsoon wind inside. So as a mitigation potential of the UHI, in fact, we also look into the wind permeability, which is estimated by the frontal area density index. And the air paths were identified based on two prevailing wind directions during the monsoon seasons, as shown on the right side. And there are two kinds of monsoon seasons. One is the northeast monsoon from December to March, and another one is the south monsoon from June to September. And it is prominent that the open space at East Singapore plays an important role in introducing the cool air into the low probability clusters at East Singapore. So we further zooming in on the East Singapore, and under the dominance of northeast monsoon, the airflow will enter the site through the offshore And in the south monsoon, it's opposite way. So the result is also matched with the wind frequency data from the nearby stations. So the further planning could be planned based on the principles of separating the UHI cluster as well as to introduce the natural ventilation as much as possible. And finally, we brought about the site-specific climate-sensitive prototypes of building morphologies. And anthropogenic heat is another key factor that caused the intensive UHI. And in Singapore, the House and Development Board built such residential buildings where most of the population live. And as we can see, the air conditioning units are placed on the outside walls in a single file and emit the heat into the canyon space. But anthropogenic heat dispersion may change during different wind scenarios, and there are maps of air temperature increment due to anthropogenic heat emission at residential areas during two scenarios. The scenario A on the left is with annual average wind speed of 7.4 meters per second at the reference height, while the map on the right is that with the minimum wind speed of 1.1 meters per second. And it is prominent that the air temperature increment due to anthropogenic heat dispersion is influenced by the wind speed and will be much higher when at the low wind speed scenario. And then we look at the unsteady simulation of the anthropogenic heat dispersion. We can see that in the center, the Newton area will always got a higher temperature increment and reach its peaks at usually 11 p.m. So with all the insight and understanding of UHI, we can overlap the UHI intensity with the distribution of vulnerable populations, and in this case, it's the elderly, to see how they are impacted and generate these urban heat risk, urban heat health risks assessment map. And here is a video. So all those above urban scale parameters and GIS-based climate modeling have been integrated into this microclimate digital platform that we developed recently. So we can choose a regular shape site of interest to do the web-based simulation. And we can also choose a irregular site to do the simulation. For example, here we are chosen the urban heat island intensity, which is estimated by the air temperature increment. And we also have like neighborhood wind permeability, which is estimated using the wind velocity ratio. And the calculation used the wind frequency data from the nearest stations. So now we got a new feature of uploading the new building massing to replace the old one. And in this case, we can do a new simulation based on the new design and got the new result as the design reference for the architects. While at the urban scale, for example, we have the urban scale wind permeability at different regions. And as such, we can perceive the potential wind corridors according to this map. This is the Paya Lebar Air Base. And we also have the anthropogenic heat dispersion maps for which we can see the hotspot. So based on these studies, we find an area of high UHI intensity, which is Newton, as shown on the left map. And we conduct more neighborhood study using high fidelity CFD simulations. As it requires massive computing resources, we also use the computational power of the National Supercomputing Center of Singapore. And with extreme weather conditions, when there is no incoming wind, the heat plumes will form the buoyancy-driven flow, which accelerates the dispersion of anthropogenic heat, as shown in this video. And it facilitates the airflow towards the center. This could be an opportunity, but also an issue. So imagine there is greenery resources around these residential buildings, then extra cooling effects can be carried. But if there is a heavy traffic around, then the pollutant particles will be carried. So how to plan the surrounding of the residential areas matters. And we also investigate how different wind velocity ratio impact the traffic pollutant dispersion. And when there is no incoming wind, the buoyancy-driven flow also dominates the traffic pollutant dispersion. So next, going down to the building scale, the building design can also impact the immediate outdoor thermal environment. And this figure on the right shows the simulation result of different design parameters and the different dispersion resource location. And the result shows that the building height variation, building separation, and building porosity, and also the heat source position, whether it's on the leeward or windward, will have different impact on the anthropogenic heat dispersion. But there is an interesting point that for example, the sky garden may not be as effective as we expected because the heat from the lower level may be trapped inside the sky garden. So sometimes when you take a walk after the dinner, you may feel hot. So this is the special care we need to take when we make the designs. And the building design also has impact on the interior spaces. We also conduct parametric studies to investigate it. And we set different building design parameters, for example, the HDB typologies, the floor elevation, and the apartment location, and also the heat emission source location, whether it's on leeward or windward. And the result shows that the case B and case C typology, if the heat source is on the windward, then it is hard to disperse, and it may even transmit into the natural ventilated apartment. So apart from the research above, we are also performing the real-time observation. We use LiDAR together with a near-ground IoT sensing network to capture the fine resolution data for both the boundary layer as well as the near-ground microclimate. And we are also working on the high-fidelity model, and together we could conduct the fine spatial temporal scale climate risk evaluation. And as we mentioned, that all our works is to build the climate resilience for the current and for the future, and also as the reference for designers to take actions in practice. And that's the end of my presentation. Thank you.
Okay, any questions from the floor?